Good morning, students. And this is the continuation of last class where we left. Okay, that is magnitude and angular velocity. We already knew that magnitude and amplitude are the more or less equal because it has the highest energy form, the point where it has the highest energy and the maxima, right? And angular velocity is the light can travel by the angular moment, which means rotational moments. That's why we call as angular velocity. Okay, and see that which can be calculated by y equal to a sine within the bracket omega t plus pi, right? We knew that y equal to magnitude of the electrical field, right? Electronic configuration or electric field of electrical energy of the wave, and a equal to is the amplitude, that is the distance in the y axis, and pi is the phase angle. This phase angle only gives the property of maxima and minima in the waves. Okay, so at last we can derive that omega equal to 2 pi nu, right? So omega, we knew that. Okay, this is the angular velocity, and you can see that the maxima and minima by the pi by 2 and 3 by pi by 2 for the rotation vectors, so it can produce maxima and minima. That's enough for us as a biotechnology students, so you should know that how the light can be traveled. Okay, then superposition of waves. When two or more waves transverse the same space, a disturbance occurs, right? When we give the two or more waves in a space, which it will gives the interference or sometimes make an amplitude also, right? So the resulted a periodic function with the same frequency but larger amplitude. If the waves are constructive, which means the phase is same exactly superimposed, means it will give the larger amplitude waves. You can see in the figure A, right? See that gray color wave 1 has the maxima at the positive side y axis, and the second wave which is in blue color also have the positive side in the same amplitude but a little bit higher but the same space, right? So the resulted is in black color waves, which is higher energy than the source 1 and 2. This is called as constructive amplification. The maximum amplitude occurs when the two waves are completely in phase. That's why we call this here in the graph, and zero, above zero, positive, negative. When the maxima and minima are completely in phase in the time period, means it will give you the amplification. Okay, whenever the phase difference between the wave is zero, which means exactly superimposed, which gives amplitude, right? Or the integer multiple of 360 or exactly 360, means, and those also gives the amplification of waves, larger amplitude of waves. Resulted waves will have the larger amplitude than the sources. It is used in laser. The maximum destructive inference occurs, okay, amplitude occurs at the zero angle or the 360 angle. Just opposite, the destruction also occurs in the equal to 180 degree or the integer multiple of 180 degree. See that? If you see the picture B, you can see that wave number 1, which is in gray color, have the maximum amplitude at the positive side of the axis, and the wave number 2 in blue color has the positive side, maximum at the negative side of the axis. So these two axes in the same space will destruct each other and give somewhat lesser energized waves. Resulted will be lesser energized, which is black in color, shown in black in color. Okay, so maximum destructive interface occurs, we already knew that. Then in superposition, what happens? A complex waveform can be broken down into simple components by a mathematical operation called, that is most important application of mathematics, that is Fourier transformation. So we are using this principle in IR, FTIR, Fourier transformed infrared rays. Okay, so we need that much amplitude for that sample analysis. Okay, now you can see that wave 1 in the picture, second picture 6.5, figure 6.5. You can see that wave 1 is have the wavelength, and wave 2 have the slighter bigger, right? Superimposition of two waves of different frequencies but identical amplification, which means frequency means number of oscillations, right? So it has a different frequency but identical amplitude, which means the height of the maxima is same. Okay, both A and B waves get constructive and produce the bigger energized waves, that is the resulted waves is shown in C, right? Okay, diffraction. So, and this is the basic principle of sunlight, where we can see the rainbow, right? All type of EMR exhibit diffraction. What is it? It means if you can see that in the picture from the sunlight, some water droplets has deflected the path, right? That is the obstacle of the light passage. So process of parallel beam of radiation is bent as it passed by a sharp barrier. Here the water droplet in the atmosphere is the barrier through a narrow opening wherever, which means, right, wherever it crosses it will get diffracted. And we also see that from the sun the rays are denoted in yellow color, which means they are plane polar are light in the same wavelength, parallel beam, right? And when it reaches to our eyes, it gives different colors because of the diffraction. So we get the visible spectrum VIBGYOR. Coherent radiation. The condition of coherent are the two sources of radiation must have identical frequency. The first thing, right? Identical frequency. We already seen that in the last slide. Then the phase relationship between the two beams must remain constant with their time. That is the speciality of coherent radiation. Phase relationship between the two beams must remain constant, which means that is called as coherent radiation. It will give more energy than the superposition. This also called a simple superposition, but is exactly 0 degree, right? 0 degree or 360 degree. 0 degree is the exact one. Okay, you can see the this is the picture. C is the picture. You can see how it diffracted the light from the surfaces. Okay, in the A picture you can see that parallel monochromatic beam, it crosses to the slit A. Diffraction by a single slit, we already saw the example of the obstacle by water molecule. In that, the second example is by slit, right? The slits has the diffraction by a single slit, which cause the radiation at the different level. It reaches to the, actually it should reaches the O, right? But what happens, there are two more slits, B and C. Okay, B and C, but it produces the dark and light bands. So it is what happened even in the photographic films. Nowadays we are not using that photographic films because there is no negative resolution, right? Okay, and this is all about coherent and transmission of radiation. The rate of radiation propagates through the transparent substance is less than the velocity in vacuum, right? This is what is it, truth, right? What we can call this a normal world phenomena, right? The rate of radiation propagates through a transparent substance is less than its velocity. The velocity is lesser when it crosses the dense medium other than a vacuum. That is the point. Depends on the kinds of the concentration of atoms, ions, molecules in the medium. the velocity of the light is mainly right. The velocity of the light is mainly affected by affected by, it gets slower, right, slower by the atoms, which means it depends on the concentration of atoms, ions, molecules in that particular medium, maybe atmosphere, water, air, glass, like that. Okay, because the frequency change is not absorbed when it crosses to the different medium, the frequency change is not absorbed. However, the interaction cannot involve the permanent energy transfer because of the density of the medium, molecular concentration of the medium, or how much the molecules are present, which means tightly, right, closer. Okay, the interaction involved in transmission is a periodic polarization. What happens in the transmission means it get polarization of the atomic and the molecular species of the medium. That's what happened in when it gets to the when it get enter into the different medium. Okay, radiation from polarized particle should be emitted in all directions in a medium, right? That polarized particles, understand that this is not a plane polarized, this is polarized. Particles should be emitted in all directions in a medium. And see that refraction and reflection of radiation, when the radiation passes at an angle through the interface between two transparent media that have different densities. We already seen that in the previous slide also, right? If when the light rays passes or AMR passes through two different medium, what happens? An abrupt changes in direction, that is called as refraction, right? Because say that because of the difference in velocity of the radiation in the two media, that again depends on the concentration of molecules present in that media. That's why we call as densities, right? Various densities. When the beam passes from a less dense to more dense environment, such as less dense is air, more dense is water, or more dense is glass, what happens? The bending is towards the normal to the interface. The bending is towards the normal to the interface, right? See that this is normal. You should say that this is dense, that is velocity of the radiation, and the bend is shown in that m1 and m2, right? In that m1 it shows the bend towards the normal one, and bending away from the normal occurs when the beam passes from the more dense to less dense medium. This process in this directions, from below to up direction, you can imagine that how it gets deflected. Okay, the extent of refraction is given by Snell's law. This is very basic law, sometimes you may ask it in gate, right? So that is nothing but sine I by sine r, we can see that this is refraction, right? Okay, we will see that. Okay, n2 by n1 are frequency between these medium. And see here, the radiation crosses interface between two media differs the refractive index, that is called as refractive index, always occurs when it passes through the two medium. The fraction of reflected radiation becomes greater with increasing differences in refractive index, right, which is given by IR by I naught. I naught is what we are giving, which is unaffected light. IR is refracted one, so which is directly obtained by n2 number of waves, right, number of maximum and minimum by that. Okay, n and n2 are the refractive indexes of the two media. Okay, so scattering of radiation, that I told you, scattering is used to find the contamination in atmosphere, or drinking water contaminations are usually the samples are analyzed by scattering, which is called a snifflometry method. Transmission of radiation in a matter can be pictured as a momentary because it has no photon, right, radiant energy by atoms, ions and molecules, followed by re-emission of the radiation in all directions as the particle return to their original state, which is scattering. When we give the light, if it reaches to any obstacle, it can re-emit, right? It may be re-emit, that is the exact word actually. I see it bends to the direction, but it doesn't cross the medium. It doesn't cross the particle. That is the main difference in scattering. Okay, but it reflected in all directions with atomic or molecular particles that are small relative to the wavelength of the radiation, and this is what we are using in Raman spectroscopy and other scattering. Okay, destructive interferences removes most of, not all, the re-emitted radiation. If it is caused destructive, which means completely is going to destroy, means it doesn't remove any re-emitted radiation except the radiation that travels in the original direction, because the source directions, when we are giving a light from X to Y, that direction will not affect because it has a positive pressure to reach the particle, right? But it can destruct the all other direction particles which is get reflected. Okay, that very small fraction of the radiation is transmitted at all angle in the original path, and that intensity of the scattered radiation increases with particle sizes, right? This is also a principle. Very small fraction of the radiation is transmitted, right? Underline the word, it is transmitted. I already told you, in this scattering there is no transmission occurs. Sometimes very small fraction of the radiation is transmitted at all angle from the original path. Actually this is not correct. I think it is not going to transmit. Here the transmission may be mean of the path length or the direction. Okay, that is maybe transmission. Okay, anyway it is not going to pass through the sample, right? Okay, because the sample may be in a metal or inert substances, it cannot pass through. Okay, intensity that have scattered radiation increases the particle size. I see that this is the most important thing. The angles from the original path, and that the intensity of the scattered radiation increases the particle size, and this is what happened in the classification of scattering. This is what we should study, the different type of scattering, like such as Rayleigh scattering, Mie scattering, right, and the Raman scattering, all those things. Okay, so this is what happens. You can understand the principle. Object incident light we are giving from the sun, that is I naught, it get reflected at the particular angle, right, at the right angle maybe, and the refraction is it crosses to the medium. This is the difference between the refraction and the reflection. And the B picture you can see that this is called as scattering. What happens, incident light, see that the direction of incident light or source path of the incident light won't get because it has the constructive, right? So but it can destruct the other directional waves. Rayleigh scattering, most important thing. And see this, if you want to know what is the basic principle behind that, why sky is in blue and why sky is red in color in sunset and which means dawn and sunrise, right? Okay, I gave that YouTube link that is wonderfully explained by the professor. You can go and see that if you have interest. Okay, scattering by the molecules are aggregates of scattering by molecules or aggregates of molecules with dimensions significantly smaller than the wavelength of radiation is called Rayleigh scattering. What is the essence, right? It is going to be scattered, but the particle size is very smaller than the incoming wavelength. Okay, the intensity of the scattering is proportional to the inverse fourth power of the wavelength, dimension of the scattering particles, square of the polarized particles. So you should remember that the dimension of particle is smaller than the wavelength of the radiation, giving radiations, right? And that scattering by large molecules. In large particles, scattering can be different in different directions, that is called as Mie scattering. So measurement of this type of radiation are used to determine the size and shape of the large molecules and collider particles. These are the application of Mie scattering. Raman scattering, and this is different from the Rayleigh scattering and the Mie scattering. This is effect differs from the ordinary scattering in the part of the scattered radiation suffers quantized frequency changes. You can see in the picture, I will explain you. These changes are the result of vibrational energy level transition that occurs in the molecules as a consequence of polarization process, right? So due to the polarization process, the vibration energy is changed. That's what we should understand in the core. Okay, this is Rayleigh scattering. See that Mie scattering by the large particles and the Mie scattering in the larger particles. What happens, we can study the molecular size or surface by the Mie scattering. In the Rayleigh scattering, what happens, the incident light have the more wavelength than the particle which is hitting. Okay, then see that this is as usual vibrational states. Infrared absorption, what happens, Rayleigh scattering, it gets excited state up to the some level of energy states, that is virtual state actually, right? But it returns to the same energy level where it is started, that is Rayleigh scattering. But come to here the Stokes-Raman scattering, what happens, the molecule get excited from the ground state level, it reaches to the some vibrational energy state, and then what happens, you can see that a green color arrow which return to the state which is slightly higher than the ground state, right? So this is the anti-Stoke, just opposite that molecule get reach the ground state beyond that original state of the molecule when the light hits. Okay, blue color of sky is due to the Rayleigh scattering, which results from the greater scattering of shorter wavelength of the visible spectrum. That's why we call it as a Rayleigh scattering, and this is identified by Nobel laureate, right, Raman, Sir C.V. Raman. The principle is explained by Sir C.V. Raman actually. Okay, polarization of radiation, very important point. Ordinary radiation consists of bundle of electronic waves in which the vibration are equally distributed among huge number of planes, which means the directions, right? Oscillation of the ordinary light has the oscillation in different directions. Okay, then removal of one of the two resultant planes of vibration in beams is plane polarized, because we need plane polarized light for our study purpose. The resultant electric vector of a plane polarized beam occupies a single plane, right? So we need that single plane. Plane polarized radiation is usually produced by the antenna, microwaves and other single excited atom or a molecule. Note that it is single excited. Okay, and this picture is to explain how the non-polarized or polarized light get oscillation in all directions. See that unpolarization in the direction in all directions, 8 directions, and after that a slate or the polarizer, maybe in the polarizer is an 8-mark question. Usually I will teach you during that polarization topic extensively, right? Okay, there we can get the vertical polarized light, so that's what we are going to use. See that other polarizer, you can see that yellow and blue color, which is two directional, but after polarization, it will plane polarization, you can get only the electronic, not the magnetic, because we are using the electronic properties. And the third picture is how the antennas are radio waves. We are hearing FM, right? That's in particular hertz, right? That hertz are produced by this way. See that red color and green color, which are perpendicular to each other, those are plane polarized waves which reaches the transmitter and we get the sound. And this is the difference between plane polarized light and polarized light. Figure A is the plane polarized because it has the only electronic wave, that is sinusoidal wave model. We already knew that. And the figure B is if it is not a plane polarized, unpolarized means how it will be. See that particle is getting more and more and getting more oscillations. At last it gets, what happens in the maxima and minima, and this is what they are exacting, this is what they are telling in the picture B, right? If it is maxima, the scattering is, sorry, the energy level is more, that's why it get amplitude and get they reach the maxima, and the minima it gets very shrunken one. And figure C is, this is the direction of, we already knew that any electronic has in a single direction, and this is the movement of particle C, figure C, figure 6.11, in that C is denote that plane polarized light of the same. Okay, then next figure you can see that is X and Y is that are the unpolarized, then after that we can get the polarization, this and all explained. Okay, phenomena of optical spectroscopy method. What is the phenomena? We already knew that spectroscopic method means we are going to measure the transmittance light, right? And we are going to conclude that what is the concentration or any other thing of the sample, right? So there are few phenomena. One is absorption, fluorescence, phosphorescence, scattering, emission, chemiluminescence. These are the phenomena used in spectroscopical methods to identify the sample or analyze the sample. Absorption, when a matter captures EMR, energy of the photon is transferred from the radiation to the absorbing species. Underline this, you can take notes. Energy of the photon, which is we are giving, right, I naught, is transferred from the radiation from the EMR to the absorbing species. Those absorbing species are called as chromophores, right? And the fluorescence means absorption and immediate re-emission of light or photon which has a longer wavelength than previously absorbed. We already knew that fluorescence gives longer wavelength because it absorbs in a shorter wavelength and it gives a longer wavelength. Otherwise we can say it absorbs at a higher frequency or with a higher energy, it emit the lower energy, lower frequency, right? Don't forget this. This is the principle wherever you are studying about the spectroscopies, or what kind of spectroscopy you should choose and among according to the instruments. Okay, phosphorescence, nothing but cold light, the same process. The process in which energy absorbed by the substance is released relatively slowly in the form of light, right? See that you can see here, the first one is normal spectroscopy, and the first picture incident light and transmitted lines. Actually I naught and IT I missed, actually I is there, but IT we should mention. And the second picture is called fluorescence and phosphorescence, right? Fluorescence is an immediate response. You should remember this seconds, how much seconds taken for the fluorescence may be asked in some other exams, not in university exams, maybe MCQs will be in this. Okay, and the phosphorescence, what happens, it get delayed because the it reaches to the some other vibration level in between that and stay there and again emit. Okay, this is called as phosphorescence. It takes that particular frequency seconds, so that's why it is called as cold light. Okay, scattering, we already knew that light rays get deviated from its straight path and striking the obstacles like dust or gas or molecules, water vapors, etc. This is what we are using for drinking water contamination, to test the drinking water or to test the dust in the atmosphere, right? Okay, then scattering of light gives rise to many spectacular phenomena such as Tyndall effect and the red hues of sunrise and sunset. I already told you about this Tyndall effect, which has happened in the colloidal particle, right? I think you are more familiar than me in your lower grades. Okay, emission, which means occurs when the excited electron turns to a lower electron orbital. See that? When the excited electron return to the lower electron orbital, the emitted radiation is termed as luminescence. This is the common name actually. What happens, right? Luminescence may be a fluorescence or the phosphorescence. And the last one, chemiluminescence, which means the light will be emitted during the chemical reaction, is called as chemiluminescence. Okay, you can get many examples for that chemiluminescence. Here I have given that what is that, eugenol, I think. Okay, and in our practical also we are going to see about that pyridine molecule of chemiluminescence. Okay, and this is just information. In the last year I think I was there in that Marina Beach. You can observe that there are luminescence produced by the waves the entire length of Marina, and that a light is moon. Actually it gets scattered in the uh, sky water, sea water, and the light blue color is the luminescence, which is bioluminescence produced by marine algae, right? If you have any idea to work on the marine algae projects, you can search it and you can work, because marine biotechnology is one of the upcoming from the days when the biotechnology coined, right? So if you want, you can research and you can choose that, because marine has that much potential, the sea has that much particle which is not explored till. Okay, I think I will close this class by slide. The next class we will see the components of spectroscopic instruments. Bye bye.